So again, when you come to the mutual induction, so what happens in the mutual induction? So we can say that over here. So if you see in the figure, I have just shown the two circuits, and in between those two circuits there is no direct connection. Yeah, so the mutual inductance between the two coil is a property of coil due to which it opposes the change of current in the neighboring coil. Obviously this is the basic property of the coil which opposes the change in the current in the coil. Yeah, so obviously that is according to Lenz's law that already we have seen. So now how the things will work in this case? So when I just obviously make this circuit on, let's say for the first one, so when I just make this switch on and the current starts to flow, now this flux, it is also linked to the secondary coil. The flux also linked to the secondary coil. That means the flux linked to the secondary coil, they are also going to change. They are also going to change, and that is the reason again you can find the induced EMF into that your second circuit, that is a coil 2 over there. So that is called as a mutual inductance. Obviously the EMF get induced into this your adjacent coil because of your change in the current in the, let's say, neighboring coil. Yeah, so they're affecting. Yeah, so that is how we can say that it affects over there. So that is what we call as a principle of your mutual induction. So the flux linked with the secondary, yeah, so definitely it depends on the current flowing through the primary. Again we can say that phi s is equals to m into ip. Again we can say that, so this phi s upon I, that is P, is equals to, let's say, that is a mutual inductance. So this is the most simple way, that is how we can write it down, the value of your, that is a mutual inductance. Yeah, so that is denoted by, again we can say that it is M. Now the next, a very important, the phenomena of mutual inductance of two solenoids. So now how this mutual inductance of two solenoids will work over here? So you have to show the two solenoids. Yeah, you have to just show these two solenoids of two different radius of that your coils over here. Yeah, so you can say, so these are the two different coils. So for one of them, let's say this is your R1, then this is nothing but R2. Again the number of turns N1, N2. Obviously we know that, so those are nothing but the number of turns per unit length. Yeah, so that is what I'm writing over here. Okay, again their cross sectional area is, let's say, A over here. The current flowing through this is nothing but I1. The current flowing through this is I2. So let's say initially the current starts to flow through that second solenoid, which I have shown by just a dotted line. So what is the magnetic field over there? So which is mu 0 n into I2. Yeah, so just we have seen the B is equals to mu 0 n2 I2. Even you can just write it down like that. Okay, now we know that, so this flux, so again we know that again, so this is your value of your B2. The magnetic flux which is linked to the first coil or the first solenoid, so phi is equals to B into A. Again further we can say that, so phi is equals to NBA. So that is also how we can just write it down over here. So the flux linked with the first coil is nothing but the phi1. Again this is, we can say that is the N1. Then this is your external, that is field, which is B2, and then this is what we can say that is a A. Then just put down those values. So this is N1. Again we can say B2 is nothing but mu 0 N2 I2 into A. So this is the value of your phi1. Further I can simplify, this is N1 mu 0, N2 is number of turns per unit length upon the length of that solenoid, again I2 into A. So this is the value of your phi1. Now again we know that, so phi is proportional to I. So phi is equals to, again for this case obviously we are just going to write it down in terms of that mutual inductance. Yeah, so obviously we can just write it down for this case. So this is nothing but mutual inductance over here. So that is, we are just going to denote it by, let's say, M12. Yeah, so this is the flux. Yeah, so obviously that is phi is equals to M12 into I. Yeah, so this is again phi1 and this is I2. So that is what we have seen over here. So again, so this phi1 that we have just write it down over here. So that is your N1, again N2 mu naught, again I2 A upon L. Yeah, and again if you want to just, that is the I2, and the same thing, so that is your M1 2 over here. So you can see that this I2 gets cancelled, and easily you can write it down now. So mu naught N1 N2 A upon L, and this is the mutual inductance which exists, yeah, for this a case of two solenoids. So this is the value of your mutual inductance for the case of your two solenoids for this particular case. So this is the value of mutual inductance for the case of your two solenoids that we have got it over here. Now similarly, what we assume initially, the value of current I2 is flowing and the magnetic field is produced along the axis for that second solenoid. Obviously that will act as an external field, yeah, so for the first solenoid. Then just obviously the flux linked with the first solenoid will get changed. We can do exactly in the similar manner opposite. So first calculate the magnetic field along the axis of first solenoid. Again the flux linked with the second one, you have to just check it out, and from that you have to calculate the mutual inductance. You will get the same expression, that same mu 0 N1 N2 A upon L. So basically now it depends on what? So this mutual inductance, so it depends mainly on this your number of turns N1 N2. Again it depends on the common cross-sectional area. So if you're seeing that, so this depends on the common cross-sectional area, yeah, inversely proportional to that length. So these are the various factors. Again the orientation, so how we are going to keep, yeah, so how is the orientation for those two solenoids, so that also important for this case. So if I just put one solenoid like this, yeah, again for the another solenoid, so if I just change its orientation, yeah, so for another solenoid, so let's say for example over here, yeah, so the same thing, so this is the first solenoid, and if I just place the second solenoid like that, yeah, so definitely this also going to affect your value of your M. So there are various factors on which the value of your mutual inductance depends.